So the ISS orbits in what they call the thermosphere. And the thermosphere is a region of the atmosphere that gets as hot as 4,500 degrees Fahrenheit. Well, at that temperature, there are very few metals or very few substances on Earth that will withstand that kind of heat without turning into, molten, just whatever. So NASA says, well, the reason that the ISS just doesn't, completely melt up there, and this is kind of a misdirection, by the way. They say, well, at that level, the air molecules are so sparse that any type of convective heat to the ISS would be non-existent because these so few air molecules are never going to pass that heat on.
The heat that won't keep you warm. The thermosphere lies between the exosphere and the mesosphere. Thermo means heat, and the temperature in this layer can reach up to 4,500 degrees Fahrenheit. If you were to hang out in the thermosphere, though, you would be very cold because there aren't enough gas molecules to transfer the heat to you.
Well, that's all fine and dandy, except that's not the issue. The issue is not a matter of how the ISS is affected by convective heat, but it is how it is affected by radiant heat.
It isn't the gases of the atmosphere that is making it hot. That isn't the source of the heat. That heat comes from the sun's radiation. Think of one of those hot metal slides on a summer day. It isn't the atmosphere that makes those things get so hot. And just because they make it shiny, that doesn't mean it doesn't get hot. Those things can really burn because of the sun's radiation.
And this is the type of heat that is hitting it directly, right? Okay. And not only would the radiant heat from the sun, supposedly, like I said, if any of this was real, which we don't believe it is, not only would it absolutely fry anybody inside, it would melt the ISS. There's no way they could possibly convect this heat away from the ISS. They just simply can't do it.
Keep in mind here that the temperature of red hot lava is usually around 1,470 degrees and 2,190 degrees. Compare that to the thermosphere's 4,500 degrees. If the sun can make super sparse particles that hot, it should have no problem vaporizing the really dense particles of a solid object. And you know how water boils at a lower temperature as you rise in elevation? Guess what? The same thing is going to happen to all of the materials that the ISS is supposedly made out of. It is all going to boil at a lower temperature at a high elevation.
During the Gemini program, engineers realized that astronauts not only needed protection from the temperatures of space, but also from the heat generated inside the suit, from their own bodies as they worked. Originally, the suit designers thought that airflow over the astronaut's body would keep temperatures regulated. What they discovered was that air cooling in a spacesuit is insufficient to do that job.
In addition to that, so you have to go back to thinking, what exactly is it that's heating up those sparse air molecules to 4,500 degrees? Again, it's that radiant heat. And along with that radiant heat comes gamma rays and X-rays, which are very lethal to human tissue. Not much can withstand that. And honestly, it would probably take a couple feet of lead to be able to shield anybody from that type of radiation. I mean, think about it. When you go to a dentist's office, they put a lead apron on you just for shooting a little dental X-ray. These gamma and X-ray radiations are orders of magnitude higher, and nobody could really survive it. And NASA just conveniently really doesn't address that. But they do talk a lot about how the Orion project is going to be trying out all this new shielding, right? So they obviously are acknowledging it.
But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space.
What? We must solve these challenges before we send people through this region of space? I thought this problem was solved over 40 years ago. when he sent a bunch of people in jumpsuits and tin cans through it there and back a half dozen times. But I forgot the Apollo guys. They were clueless regarding the radiation belt. That it didn't affect them.
I don't know the distance to the Van Allen radiation belt, and if we did, it wasn't a problem. If we were going to encounter it, then we would have had to build the spacecraft and the spacesuit to not give humans a problem. You don't just build something and hope it works. You study to see what the threats are, the environment is, and then you say, how thick do I have to make the metal on the spacecraft so that going through this kind of radiation or these kind of meteoroids, it won't get hurt. And then we build it that way.
I know they're talking about the Van Allen radiation belts here, which are a little different than the thermosphere, but we see the same kind of attitude here when it comes to handling the radiation.
I help manage the Orion Crew and Service Module office. We're responsible for developing the crew capsule, which is where the crew lives and works when they're in space, and the service module, which is what provides the power and the fuel and the consumables then that is plumbed over to the crew module. We don't have the ultimate answer for radiation on Orion. We're still working on that. If we were to build Orion out of the materials we need and the sole job was to protect for the radiation environment, the vehicle would really be too heavy. So we have to balance the weight of the materials that we put on the spacecraft with how much protection it's providing the crew. So we're really looking at it from an operational perspective. If we understand a radiation event has happened, the crew will actually take shelter in the aft bay of the vehicle. We have found over the years that water is a really great radiation absorbing material. So we could do things like water that's already there in the water bags for drinking and things like that. That water could be used to shield them. As well as we had some concepts like a water-filled vest that they could put on should they know there's an event and need to be protected.
We don't have a clue when it comes to like how to protect them from like radiation. So we're gonna just like put them up there in like water suits. Yeah, we like water suits, and like we put water all around them, so the radiation could go like into the water, and then they could drink it, and it could be like a Fantastic Four. Everybody they'll come back and be mutants when they get back. But we just got some ideas, yeah. But don't worry about it. Yeah, I know there are refugees everywhere, and like people are starving and stuff, and like we have homeless all over the place. But if we spend like a few $1 trillion, I think we should be able to figure out how to make water suits for the astronauts in space, and then maybe it'll work out like it did for the guys in Apollo.
The belts are 1,000 miles to 25,000 miles above the Earth.
We went right out through them.
No effects on your cells?
We didn't even know it. I don't think anybody, maybe somebody said you went through the radiation belt, but we didn't feel it inside, and we didn't get any, added radiation.
Yeah, if you pretend that it's not really there, then you can just go right through it.
I'll never forget the moment that everything clicked. And that was on a Friday night. I was just watching videos, doing my typical thing, just wondering, trying to prove these things wrong that I was seeing. And I don't remember what video it was, but the narrator in the video said, how are there satellites and a space station in the thermosphere layer of the atmosphere when the temperature gets up to 2,000 degrees Celsius? That's where the majority of LEO, which are low Earth orbit satellites, and the International Space Station and the Space Shuttle used to be. What they used to, the Space Shuttle used to be, but everything else orbits the Earth. And so when that hit me, I said, wait a second. This can't be. How does heat that builds up inside the space station get out? Right? Inside the space station you have astronauts, which the temperature of a human being is 98.6 degrees Fahrenheit, which is warm. I'm familiar with that scale, living in the United States. And that's pretty warm. That's actually hot. If it was 98.6 degrees in this room, I would be sweating, and so would the astronauts.
When it's hot out, it isn't enough to just let the liquid circulate inside of you. You've got to bring liquid in and let liquid out. Without that, your body will overheat. Your body has to get rid of the heat. It doesn't just go away by getting circulated around inside of you.
During the Apollo era, it was decided running cool water through a garment that covers the body could help keep the astronauts from overheating. The means of cooling the astronaut was now an essential life-sustaining element to the spacesuit and was here to stay. The spacesuit currently in use on the space station, developed in the 1970s, also uses a water-cooled garment. Circulating water is still the best way to cool an astronaut.
And when that water warms up by the same factors that are warming up that body, and that heat has no place to go, that astronaut is in trouble.
The spacesuit cooling system needs to do more than just circulate water. As the astronaut works, their body generates heat, which is transferred into the liquid cooling and ventilation garment. A thermal control loop needs a way to remove the heat from the water that is circulating through the system. That's where SWIMMY comes in, the spacesuit water membrane evaporator.
SWIMMY consists of some porous hollow fiber membranes that are contained in a metal manifold. When warm water flows through the porous membranes and then is exhausted into space, the cool water continues through the porous fibers and continues to flow through the LCVG liquid ventilation garment to cool the astronaut.
All right, so they agree that the astronaut has to get rid of the heat, and they said they do this through an evaporator, which they say exhausts the heat into space. But where is the exhaust port for this evaporator? Do you see one anywhere? That looks like a pretty closed system to me. You'd think there'd be quite a bit of exhaust coming out of that thing if the moon was 250 degrees during the daytime, as NASA claims.
How does the heat get out of the station if there's nothing to dissipate it through? Right? There's no collision. There's not enough collisions with these particles to transfer heat into the station. So how does that heat get out? It would be really warm, if not hot, inside the station. And another thing to think about is these black lines here are supposed to represent the solar panels on the ISS. Solar panels absorb light to create electricity. And they can work in 1500 degrees Celsius temperatures. That's very, very hot. And okay, let's say they can. And they're getting hot and they're connected to the station. Shouldn't they be transferring heat into the station? I mean, through the matter that they're connected with? So going back to the electromagnetic waves and light's all is hitting these satellites, but they don't get hot. But if these gas particles absorb light and energy and get warm, these satellites are made of metals and very dense matter, and they're cool. They're going to absorb that light too. How do they not absorb the light? How does it choose to only warm the atmosphere but not the satellites and not the Apollo spacecraft or not any of the probes that have been out in space that are getting hit by direct sunlight? It doesn't add up to me. It defies logic.
It is the same thing with the ISS. It is all a closed system. According to the I.S.S. National Laboratory, there are 3 forms of cooling on the space station: radiators that release heat, air conditioning, and reflective paneling. The reflective paneling reflects heat away from the station. The air conditioning circulates the air inside the station. Radiators draw heat out of the space station to keep the station cool. That is seriously all they tell you. It would seem they just expect you to take their word for it. So how does a radiator work exactly?
The way your typical radiator works is you have hot coolant that comes in one end tank. The coolant travels across the core and exits out through the other end tank. And at this side, it's cooled down. As the coolant progresses across the core, it is transferring heat into the aluminum of the tube from the coolant. Once that heat goes into the tube, it is then transferred to the fin, where it then exchanges the heat with the air that is moving through the radiator. As that coolant goes through the rest of the core, it is going to get progressively cooler until it reaches your end tank and then exits.
Okay, so a radiator works by transferring heat into the air. But the ISS doesn't have any air to transfer that heat to. If there is no air traveling through the fins, that radiator is just going to get hotter and hotter until it melts down. That definitely makes you wonder what exactly they claim their radiators are made out of that can handle such extreme temperatures.
When you're dealing with radiant heat, and you are looking at what the ISS is made of, the carbon, titanium, aluminum, composites, stuff like that, really what it is ideal for is to create an oven. So that's exactly what's going on. The crew would be cooked. It's simply not possible to do this. They have no reasonable explanation for how the ISS can be flying around up there, let alone anybody surviving on it. And then there's questions about the electronics. It just goes on and on and on and on. But we'll kind of leave it at that.
This message has been brought to you by Bob Nodell from the Globebusters and the Flat Earth Institute of Science. Thank you all for watching. We can do this.